In this video, we shall prove the all-important implicit function theorem. The implicit function theorem is probably the best application of the inverse function theorem, and it's also the starting point of manifolds, the theory of manifolds. We will also use the implicit function theorem to study optimization problem, Lagrange multipliers. These are the various applications of this theorem. Since this theorem is very important, let's motivate what this theorem is trying to say by a concrete example. For that, I need a basic definition, that of a graph. All of us are familiar from middle school where we took a graph paper and plotted various functions like x squared by hand. So the graph, the notion of the graph, it is just the set of points in the graph paper that we actually draw. So we make this precise in the following manner. Let f from u to Rm be a function. The graph which is usually denoted by capital gamma of f, this is just defined to be the set of all points x comma f of x. If you recall, this is what we actually plot in the graph paper, such that x comes from u. So you look at all the pairs x comma f of x and put them together into this set. Obviously this we can view as an element of R m plus n. Okay, so the graph of a function from an open subset of Rn to Rm is just the collection of points x comma f of x such that x comes from u. So we just note down for specificity that the graph of f is a subset of R m plus n. Okay, now we are going to illustrate a concrete version of the implicit function theorem with the all familiar unit sphere in R3. All of us know that the unit sphere in R3 is given by the equation x squared plus y squared plus z squared is equal to 1. Okay, now note this is the sphere, that is essentially just the boundary of the unit ball. The interior part is not there in this set. So we are looking at the set which is classically called S2, sphere of dimension 2. This will start to make sense once we define manifolds, so what this dimension is. So but the classical notation is S2 for this object, and of course S1 denotes the unit circle and S3 will denote the unit sphere in higher dimensions in R4. Okay, so S2 is defined to be the set of all points x, y, z in R cube such that x squared plus y squared plus z squared equal to 1. Fine. So pictorially this object is nothing but the unit sphere, which looks like this. Of course what I am about to draw is badly drawn, but you get the idea. Now you should think about why we cannot exhibit S2 as the graph gamma f of a function. You cannot find a single function such that S2 is the graph. Think about this carefully and try to come up with a solid reasoning as to why this is impossible. However, pieces of S2 you can write down as a graph. How does one do that? Well, observe that this upper hemisphere can easily be written down as the graph of a function which is defined on this open set in R2, this bit, which is essentially the unit disk. Okay, so denote D to be xy in R2 such that x squared plus y squared equal to, or sorry, less than 1. This is the open unit disk. This notation, this D with another line is borrowed from complex analysis. Open unit disk in R2. In complex analysis, this object D is probably the most important domain on which complex functions are defined. So we have a specific notation for that, and you can consider the upper hemisphere of this unit sphere in R3 as the graph of a very simple function. What is that function? Well, consider f from D to R, the function f of xy is nothing but under root 1 minus x squared minus y squared. Okay, so here, to emphasize that I want the upper hemisphere, let me put a plus sign to emphasize that this is the positive square root. Okay, so this function, again I'll put a plus here so that it's it'll become convenient in a moment. So this function's graph is clearly the upper hemisphere. Okay, in an analogous way, I can get the lower hemisphere as the graph of the function f minus xy is equal to the negative square root of 1 minus x squared minus y squared. So every positive real number has 2 square roots. So I take the positive square root for the function f plus and the negative square root for the function f minus. Okay, now fairly easy computations will tell you that this is the graph of this is nothing but the upper hemisphere and the graph of this is nothing but the lower hemisphere. So it looks like we have it's impossible to write the entire sphere as the graph of a function, but we have managed to write the unit sphere S2 as the union of two graphs. Oh, wait a second. Think carefully. If you look at this picture, this f plus the graph would be this upper part minus this equator. The equator will be missing, and the same thing is true for the lower, the graph of the lower hemisphere. That function will take, the graph will consist of all the points here, but not the equator. So we have missed out all the points of the equator, but fear not, we can write those points also as a graph, except we change the domain. What we do is, so if we draw the three axes, essentially what we have done is the upper hemisphere we have represented as the graph of the domain D, which is lying in the xy plane, right? Well, there is nothing stopping us from considering the unit disk on the yz plane or the xz plane and considering graphs over that. It's just essentially we are just changing the base axis and what we are plotting. So this is really nothing happening in a substantial way. It's just the same concept. So what we can do is we can define more functions. We can look at the functions g plus or minus y. You can consider the functions g plus or minus xz, which is just again plus or minus under root 1 minus x squared minus z squared. Okay, and consider the graph of this function. So the graph of this function will look slightly peculiar. So this for concreteness, let me write gamma of g plus. This is just going to be the collection of all points x, g plus xz, comma z. Okay, such that xz satisfies x squared plus z squared less than 1. So what we have done is we have not just considered the graph as a function of xy, we are now considering the graph, the function is a function of xz, and it is a graph in this sense that the middle variable y has the function in it. So there is nothing really sacred about z always being a function of x and y. So we can treat y also as a function of x and z. Okay. So now we have two more graphs, one coming from G plus and one coming from G minus. And if you think about it, it looks like we have covered all of the sphere, but no. So if this, in this picture, so if this is the x, this is the y, and this is the z, we have managed to write down the left and the right hemisphere. So the right hemisphere would still be a graph, and the left hemisphere will also be a graph. But again, this what do you say, this equator, the equator along the xz plane or whatever, that will be missing from both these graphs, but they are there in the graphs that we have already done. Not quite, 2 points will be missing. 2 points will be missing. Those are the 2 points that are there in the intersection of both these great circles. So essentially this point and this point will be missing. But again, fear not, we can remedy this situation quite easily by considering two more functions, h plus minus. This time I'm going to consider yz, which is equal to plus or minus root of 1 minus y squared minus z squared. So I want you to mull over this example for some time and convince yourself together the graph of these 6 functions will, the union of this will be exactly the unit sphere in R3. So we have not managed to write the unit sphere as the graph of a single function. That's simply impossible. But what we have done is we have managed to write it as the union of the graph of 6 functions. So locally, every point on this sphere is the graph of a function. And this observation will lead on to the definition of a manifold quite soon. But before that, let's see what is it that we have managed to do using this discussion. Well, if you look at this, x squared plus y squared plus z squared equal to 1, what we have essentially said is this equation implicitly defines several functions, and we have explicated these implicit functions. Okay, so you must have come across the term implicitly defined function when you studied multivariable calculus at a basic level. So what we have done is, from an implicitly defined function via this equation, what we have managed to do is we have managed to construct several functions out of this. So the question now follows, if you have a function f from, let's say, u to r for simplicity's sake. Suppose you have a function from u to r. We will be considering a more general scenario when we study the implicit function theorem, but for the time being, just consider the function f from u to r. Does the equation f of xy equal to 0 implicitly define y as a function of x or vice versa? Suppose you have a function f from u to r and you just consider the equation f of xy equal to 0. Does it follow that you can write y as a function of x? In a more geometric way, what this is asking is, suppose you are given f of xy equal to 0 and you consider the 0 set of this function, that is a collection of all points xy such that f of xy equal to 0, then is that 0 set a graph? That's a geometric way of looking at this. Well, let's look at a simple function for which this will not be true. Consider f of xy to be xy, and look at the equation xy equal to 0. Look at this equation. Now, no simple manipulation like what we did for the unit sphere is going to obtain y as a function of x or vice versa. That's clear. We can actually make this precise. Okay, so suppose g from R to R is a function whose graph is precisely x comma y such that xy is equal to 0. Oh, sorry, what I wrote down is nonsense. Such that x times y is 0. So suppose you could write the collection of all points xy such that the product is 0 has a graph gamma of g. Then just think about what this graph is going to look like. It's just going to be the union of the x-axis and the y-axis. Okay, so which means that if this is the graph, it near any interval of 0, at this point, at least at this point 0, the graph will have to be multi-valued. So g, this is not possible because g of 0 is going to be multi-valued. Okay, so there is no clear way. It's very easy to define this function g away from 0. You just set a g of x equal to 0. So that will give you this portion and this portion. But at the origin, you need to obtain this entire thing as the value of g of 0, which is nonsense. No such function exists. I mean, the term multi-valued function itself makes very little sense. Functions are by definition single valued. So the multi-valued function is what is called an oxymoron. Such a thing is simply not possible. So we are not able to solve xy equal to 0 and get a graph. So the implicit function theorem gives you a precise condition on f of xy which allows us to extract a graph from this function, at least locally. What goes wrong with the function xy at the origin is the fact that the gradient is 0, as you can check. The moment the gradient is not 0, then the implicit function theorem will allow you to extract a graph out of it locally. So we are going to now state and prove the implicit function theorem. It's going to be a straightforward consequence of the inverse function theorem, but there is a trick involved in the proof. So let's go on to the statement of the inverse function theorem and prove it. So implicit function theorem. So the statement is as follows. Let U subset of Rn plus m and f from U to Rm be a ck smooth function. So the reason why we wrote down U as a subset of Rn plus m instead of in a weird way is to make notation simpler. Some people just write U as a subset of Rn and f from U to Rm, then you'll have n minus m and all that. The way I have written it down, the notation will become cleaner. Now we are going to denote a point. We will denote a point z in U by x comma y, where x comes from Rn and y comes from Rm. So we are going to split the variables on which this function f depends into the variables coming from Rn and the variables coming from Rn. So the first n we have clubbed together and called it x, and the remaining we have called it y. Let x naught y naught in U be a point such that f of x naught y naught is 0. So consider a 0 of this function. Denote by dy. So this is a new notation, partial derivative with respect to the variables y. Dy of f of x naught y naught. Well, what is this? Well, this is just a linear map from Rn, it is a linear map from Rm, sorry about that, Rm to Rm. This is a linear map from Rm to Rm. This is the derivative map, map of the function y maps to f of x naught y. Okay, now observe that this map will be well defined in some ball in Rm that contains the point y naught, because U is an open set. So let me just emphasize that always there's a global remark that U is always open, but let me make that precise. So because of the openness of U, this function y maps to f of x naught y is well defined in some open set that contains the point y naught. So which is well defined in some open set that contains y naught. Okay, so this map we are assuming denote by dy the derivative. Of course, this derivative will exist because f is a ck smooth function, so the derivative will exist. Okay, so derivative of the function at y naught. Of course, that's crucial. I have not specified what the point is. Okay, suppose dy x naught y naught is invertible. So this is a linear map from Rm to Rm. I'm going to assume that this map is invertible. So this is the precise condition that allows you to write the zero set of f as a graph. So the conclusion unfortunately has to come in a different page, but the conclusion is long. It is unavoidable. Then number one, or rather then we can find number one, open sets V subset of Rn and W subset of Rm such that this V cross W is contained in Ru and x naught y naught is there in this product neighborhood V cross W. Number two, a ck smooth map. So the first part is trivial, that just the openness will give those neighborhoods V and W, these open sets V and W. But the second part tells you there's something special about this V and W. We can find V and W with some special properties. We can also find a ck smooth mapping, which I'm going to call phi, from this V to W. Note this is a ck smooth mapping such that phi of x naught is equal to y naught, and I'm going to quantify that the zero set can be written as a graph of the variable x, y can be written as a function of y, y can be written as a function of x, and that is made precise by saying, and if x comma y in V cross W, then f of xy is equal to 0. That means if you look at the zero set of f, which is also within the product open set V cross W, this can happen if and only if phi of x equal to y. Okay, so at this point it's appropriate to draw pictures to illustrate what is happening. Well, essentially what is happening is, suppose, let's just for argument's sake say that we have only two variables, and let's say this is the zero set. This is the zero set of this given function f. What it is saying is that at a given point you can find a product neighborhood. You can find a product neighborhood in which you can establish the zero set. You can establish the zero set as the graph. as the graph of a CK smooth function. So this may not be globally true. So what can happen, for instance, is that it could happen that this function 0 set turns back and comes back inside. Okay, so you may not be able to globally do this. There is no way to now write the 0 set as a global function, but by shrinking this v cross w, we can still see that it's going to be a graph of CK smooth functions locally at least. So the conclusion of the implicit function theorem is a local conclusion. This is not surprising because the conclusion of the inverse function theorem was also local. So you cannot determine the global property of a function just by knowing that one partial derivative with respect to the variables y is invertible. Okay, so there is one more part to this conclusion. Furthermore, d phi x, you can write down the derivative of d phi x, and you must have done this in the one variable case when you studied implicit differentiation informally. This is the negative of dy of f of x comma phi of x. So that is, you take there's an inverse, so you take the derivative with respect to the variables y at the point x comma phi of x, and then invert the derivative, and this has to get multiplied by the derivatives with respect to the x variables also taken at the point x comma phi of x. No inverse here because we don't even know that this is invertible. So where dx f x comma phi x is the derivative of the map x maps to phi of x comma phi of x. Okay, and dy of x comma phi of x is the derivative dyf. Okay, is the derivative of the map y goes to dxy taken. So here I made a mistake. This is x goes to f of x comma phi of x. Okay, taken at x, the derivative taken at x, and here it is the map, derivative of the map y goes to f of xy taken at the point x comma phi of x, or rather taken at the point phi of x. So x is fixed here, and you consider the map y going to f of xy and take the derivative at the point phi of x. Not very different from what we did to define dy of f of x naught y naught. Okay, so this final conclusion is a bit subtle. You have to understand what exactly is happening. We'll come to that in the proof. Okay, now let's go to the proof. The proof is not hard. So before that, let me make one more remark. The statement of this theorem is rather complicated. The way I've written it, it's actually 3 slides. But what it is essentially saying is fully illustrated in this picture. So it says that roughly, if you have a CK smooth function such that derivatives with respect to some variables is non-singular, that just means that the derivative with respect to some variables is invertible, then the 0 set can be locally expressed as the graph of a CK smooth function. That's essentially what the implicit function theorem is saying in mathematical English. The variables with respect to which the derivative is non-singular, they are the dependent variables. So here we were writing y as a function of x, and the rest of the variables are the independent variables. Now, one remark, the way I have stated this theorem, you notice that this will not, if you look at the previous example, we wrote the middle variable as a function of the first and the last. So it will not happen in general that the final set of variables will be the dependent variables and the first set of variables will be the independent variable. That was usually not the case. What will essentially happen is that some set of variables will be dependent and some set of variables will be independent. This is just essentially the same scenario as what we are considering. We are just renumbering the coordinates. So it can happen that the second, the third and the fifth variables are the dependent variables and the other variables are the independent variables. So this is just a minor variant of the implicit function theorem. I'm not going to dwell too much on that because it's just a slightly notationally complicated thing, but the idea is exactly the same. Okay, so we are going to move on to the proof of the implicit function theorem. And the proof is somehow manufacture a function from Rn plus m to Rn plus m whose derivative at some point is invertible. So we are given this function f and we know that dyf at x0 y0 is invertible. But we cannot really apply the inverse function theorem because f happens to be a function from Rn plus m to Rm. Okay. Now this dyf x0 y0, the way it is defined, this is going to be a linear map from Rm to Rm. So there are n variables missing in the codomain of the function f. Somehow we have to increase the codomain by m variables. So what is the simplest and most natural thing to do? Well, fill in the missing variables exactly as they are. What do I mean by that? Define g of xy from u to r n plus m by g of xy is equal to x comma f of xy. So the variables that are missing in order to apply to make both the domain and codomain equidimensional, you just tag it along in the first coordinates of the codomain. Just tag it along. So this is the simplest thing we can do. This is a CK smooth map. That's very easy to check because f is already a CK smooth map and we have just tagged along essentially just the identity function in x. So this is going to be a CK smooth map. What is its derivative? What is its derivative? That is the key, right? We want to somehow by hook or by crook apply the inverse function theorem. So for that we need to find out the derivative, and I'm going to make that your headache by simply saying that check that dg x0 y0 is invertible. Okay. So I'm going to, I will give a proof. I'm going to leave one part to you. You can compute the derivative map as a matrix and see that it's invertible. What I mean by that is you already know that the submatrix which is going to be contributed by f, that's going to be an m cross m invertible matrix, and this part is essentially going to contribute the identity, and you can use the properties of determinant to actually check that the matrix of dg x0 y0 is going to be invertible. I will give a proof that does not depend on matrices. It's a direct proof. So let's directly prove that the derivative of gxy is going to be invertible. So what you do is let h comma k be vectors in Rn cross Rm. Okay, and choose them to be really small so that this g of x plus h comma y plus k minus g of xy. So this first part should be well defined, g of x plus h comma y plus k. Choose h and k so small. Now if you just look at the definitions and notice what will happen, because x plus the first few coordinates of g is just going to be x plus h minus h, this is going to be just h, and the second coordinates is going to be f of x plus h comma y plus k minus f of xy. Okay, now because this f is differentiable, we can write this as dfxy acting on the vector h comma k plus a small error term ehk. This is just the differentiability of the function f. Okay, so E is sublinear, where E is sublinear and comes from the definition of the differentiability of f. Okay, now it follows easily that G is differentiable, and the derivative of G is hk maps to h comma dfxy acting on hk. So this is exactly the remark I was making in the matrix proof. You will get a submatrix which is going to be contributed by the derivative of f of xy, and another submatrix which is essentially going to be the identity mapping. So identity matrix, this is just the coordinate independent way of saying the same thing. I'm just saying the same thing without using matrices, not really coordinate independent, without using matrices. Okay, so we want to show that this map is actually invertible. So what I'm going to say is, suppose this derivative map h comma dfxy hk, suppose this is 0. So essentially I'm trying to find out the kernel of the map and show that it's going to be just 0. Immediately we get that h is 0, and we also get that dfx. Okay, just a minor modification. I'm interested only in the point x0, y0, right? Because I want to show that it's invertible there. In any case, I have data about the submatrix or portion of the derivative d fx0, y0. So it follows that d fx0, y0 acting on hk is also 0, but h is 0. So this is essentially just saying that d fx not 0 comma k is 0. Okay, now I leave it to you to observe that this map dfx0 y0 0 comma k, this is nothing but the derivative of the map y maps to f of x0 comma y. Okay, I want you to check that. This is a rather trivial. This is just the derivative of the map y maps to f of x0 y0, which is invertible by hypothesis. Okay, I want you to check this precisely what this is saying. Now conclusion is that kernel of derivative of G at x0 y0 is set with 0. And by basic linear algebra, this just means that dg x0 y0 is invertible. It's non-singular. Now the inverse function theorem says G is locally a CK diffeomorphism at this point x0 comma y0. Okay, let's say G restricted to H is a diffeomorphism. It's a diffeomorphism where H is a subset of U and x0, y0 is contained in H. So we are just choosing an open set. We are just choosing an open set in which G is going to be a CK smooth diffeomorphism. Okay. Now what we do is let V subset of Rn and W subset of Rm be such that x0 is in V, y0 is in W, and V cross W is a subset of H. Okay. And define Z to be the image of V cross W under G. Okay. Now because this is a diffeomorphism, because G is a diffeomorphism, then Z is an open set in Rn plus M. Think about why this is true. This just follows because it's a diffeomorphism, and this set contains the origin that contains 0. Okay. Let H from Z to V cross W be the CK smooth inverse. Smooth inverse of G. Okay. Now here is the crux. H of xy is of the form x comma psi of xy. Because G is of the form x comma f of xy, H of xy, the inverse, must be of the form x comma psi of xy, where psi from Rn plus M to Rm is CK smooth. Okay. Now this psi is this is not from Rn plus M to Rm. This is from Z to W, because we know the domains of G and W, G and H. This is from Z to W. Sorry about that. So this psi from Z to W is a CK smooth map. Okay. Now here is the crux of the proof. Observe that G of xy is of the form x comma 0 precisely when f of xy is 0. Right? I'm writing down a bunch of triviality, so don't get overwhelmed by this. This means that the precise choice of phi of x is to just define it to be psi of x0. So this is the crux of the proof, and really there is nothing I can do to explain it, because it's actually a triviality when you realize why this is the only choice for phi. So I want you to sit under a tree and look at the nice blue sky and figure out why is it that phi is the nice and appropriate choice that we need to finish this theorem. But I'm not just going to leave it dangling in the air and let you finish the proof. Let's just confirm this. So let us check this. Let us check this mathematically. I want you to think about why this is clearly true when you think about it intuitively. Now, of course, phi from this function phi from V to W is obviously CK smooth. It's obviously CK smooth. No questions about that. The issue is the condition that f of xy equal to 0 and xy in V comma W if and only if y equal to phi of x. So to confirm that, suppose xy is in V cross W and f of xy is equal to 0. Suppose you take a 0 of this given function f, we want to confirm that y is equal to f of x. Okay. then this just means g of xy is equal to x comma 0, right? That's just by definition. And that just means phi of x, which is just defined to be psi of x comma 0, has to be y. Okay, and this is all just by definition. So really, as I said, this is nothing but a triviality. On the other hand, suppose for x in v, we have phi of x equal to y, then that just means that psi of x comma 0 is y. Psi of x comma 0 is y, which means h of x comma 0 is x comma y, which means g of x comma y is x comma 0, okay, which means f of xy is 0 as required. So this entire proof is just unraveling the definitions of what g, h and phi are, and that will give it. Of course, this phi of x naught equal to y naught is also done. Okay. So only thing that remains to be done is to show the formula for the derivative, but from what we have established, we know that phi of x comma phi of x is the identically 0 function, okay, for all x in v. That just means the derivative of this map is identically 0. But what is the derivative of this map? By chain rule, the derivative of this map is nothing but dx f of x comma phi of x plus dy f of x comma phi of x d phi of x. This just follows from the chain rule, and which I want you to check, and we know that this has got to be the 0 map, and the formula follows. The formula for the derivative follows. Okay, so this concludes the proof of the implicit function theorem. It's a consequence of the inverse function theorem. So let me also remark that in some treatments, you first establish the implicit function theorem and obtain the inverse function theorem as a corollary. But in my opinion, that's not the correct way to go about the proof, simply because the way we have done it, this will generalize to other situations, for instance, to infinite dimensional non-vector spaces, which we briefly talked about when we talked about higher derivatives. So this approach is sort of the natural one to first establish the inverse function theorem, either using Newton's method or by the contraction mapping principle, and obtain the implicit function theorem as a corollary. Now, there are new approaches to the implicit function theorem in recent times that give a completely elementary proof that does not rely on any sophisticated theorems like the Banach fixed point theorem, the contraction mapping principle, Newton's method, and so on. These proofs, however, are still long. There are no simple proofs of this theorem that are short as well as elementary. Anyway, the rest of this course is essentially a big application of the inverse and implicit function theorems. In the immediate application, in the next video, we will fix that part about the tangent space of a hypersurface. We will prove that the tangent space of a hypersurface is going to be an n-1 dimensional vector space. That's the first application of the inverse function of the implicit function theorem. This is a course on real analysis, and you have just watched the video on the implicit function theorem.